Rockets leave more than smoke. They leave pieces behind them. Some pieces fall back to Earth. Others vanish into the ocean. But many never come down. They float silently for years, even decades. At orbital speed, even a fleck can cripple a satellite. This is the unseen wake of every launch. We picture space as vast, but near Earth, orbits are crowded and finite. Think of it as a highway. More traffic, more risk. In space, crashes multiply into clouds of shrapnel. So what if every launch had to include debris cleanup? Ahead, the real costs. Second-order effects, law, power, feedback loops, and the thin line between cleaning space and controlling it. We'll follow the chain from first-order changes to long-term equilibrium, and what breaks when things go wrong. The visible problem is already significant. Tens of thousands of objects are tracked from the ground. That means bigger than a softball. Below that size, there are millions more. Small, but still catastrophic at orbital speed. In 2009, a defunct Russian satellite hit an active American one. Both were destroyed, spawning over 2,000 trackable pieces. In 2007, China destroyed an aging satellite in a test. It created one of history's largest debris clouds, over 3,000 objects. Much of that debris will persist for decades to centuries. New rockets often plan deorbit burns. Satellites retire to graveyard orbits, but legacy debris still circles overhead. Stopping new junk slows growth. It doesn't clean the stock. Meanwhile, mega constellations multiply collision risk by sheer numbers. The problem is distributed across many actors, so the solution must be too. Quick pause, tap like to help more people see thoughtful documentaries like this, and drop your take on cleanup rules below. Subscribe for more if-verse deep dives. Now, back to the unseen mechanics shaping orbit. If every launch needed cleanup, one model adds a chaser craft to capture the upper stage, then both deorbit and burn up together. Another option, prove removal for each satellite launched, or pay into an international fund scaled by mass, orbit, and expected debris. The fund hires specialists to remove high-risk objects. Cleanup hardware adds mass and complexity. More mass can mean less payload, or a pricier rocket. Big government missions may absorb the cost. For small launch and small-sat firms, small increases can be existential. Some will move to looser jurisdictions. Flags of convenience for rockets. Jobs, capital, and know-how shift accordingly. Policymakers face a real trade-off. Cleaner orbits versus homegrown growth, but the rule finally internalizes costs long pushed onto a shared orbit. The question is whether we can afford not to. Mandated cleanup creates a market for in-orbit services. Companies design, build, and operate cleanup craft. That means jobs across engineering, software, and operations. Expect a race, arms, nets, magnetic capture, even harpoons, each with trade-offs. Competition could push costs down, or consolidation could concentrate power. A few firms could gatekeep access to cleanup, and thus to orbit. Nations with service fleets gain leverage. They could sell services to others, but the same tech can approach, inspect, and grab active satellites. Close approach expertise becomes a strategic asset. Alliances may form around who has it and who doesn't. Ambiguity fuels suspicion. An environmental fix becomes a new arena of power. A cleanup mandate hits a web of international law. By treaty, each nation retains jurisdiction over its space objects. Even tiny fragments remain someone's legal property. Touching or deorbiting without consent can violate sovereign rights. Who grants consent when the owner is gone, or records are lost? The launching state may no longer exist. Ownership can be murky. Nations would need new agreements on salvage, ownership, and liability in orbit. Even a lawful cleanup near sensitive assets can look threatening. Mistrust can escalate from protest to sanctions. Verification, plans, observers, shared telemetry is essential. Negotiations take years. Debris won't wait. Cleanup is as much diplomacy as engineering. Cleanup adds mass, reducing payload or raising cost. Pressure rises to make systems lighter and cheaper. Cut corners and the fix becomes a new source of risk. A failed capture can tumble, or collide and fragment. Launches are rising fast. Can cleanup keep pace? If removals lag, totals still rise. So phase in rules, certify reliability, and cap debris per launch. Design details are the difference between stability and spiral. When stakes are orbital, failure modes matter most. We have to engineer the failure paths, not just the headlines. The ultimate risk is a Kessler cascade, proposed by NASA's Donald Kessler in 1978. Once density crosses a threshold, collisions self-amplify. Orbits can become impassable for decades. Services we rely on would falter: navigation, communications, forecasting, and climate monitoring. A sudden shift from usable to hazardous. Cleanup is insurance against collapse. Much legacy debris came from early US and Soviet activity. Many argue the polluter should pay, but collecting historic costs is often impossible. A shared fund, prioritized by risk, is a pragmatic bridge. Fix one node, pressure moves elsewhere. Well-designed rules lower cascade risk, but they can raise costs and shift industries. Favor simple, fee-based systems tied to mass and orbit. Scale burden so small players aren't crushed. Mandate proven tech and strict reliability standards. Grow a global fund to tackle the worst legacy objects. Add oversight to prevent dual-use misuse. Pilot first, learn, then scale globally. Orbital space is a commons, like air and oceans. Linking launch rights to cleanup duties enforces shared responsibility. Done well, it drives innovation and reduces risk. Done poorly, it makes orbit fragile. If this breakdown helped, hit like, add your thoughts, and subscribe for more evidence-first what-ifs. Your support lets us keep these stories rigorous and ad-safe. The final question isn't whether to clean space, but how to keep it clean for generations. Small policy choices today set the boundary conditions for tomorrow's possibilities. Design for failure, reward reliability, and align incentives so removals scale faster than launches. Because when things go wrong in orbit, they go wrong for everyone. What scenario should we explore next? Share your ideas below. You've been watching Ifverse, where imagination meets possibility. See you in our next reality.